In the previous video series, we explained that for nearly 50 years, Voyager 1 and Voyager 2 have been traveling beyond the edge of our solar system. These remarkable probes have sent back data no one thought possible, built with 1970s technology. Their computers have less memory than a modern car key fob, and they record data on an 8-track tape machine. Their continued operation is a testament to the ingenuity of the engineers who keep them talking to us across billions of kilometers. But the Voyager's journey into interstellar space has revealed the limitations of their design. Their instruments, built for planetary science, are not optimized for this new frontier. And so, building on this incredible legacy, scientists are now proposing a new mission, one designed from the ground up for interstellar exploration, Voyager 3. Unlike its predecessors, this new probe would be a true interstellar sentinel. It would carry state-of-the-art instruments to analyze the galactic wind, powered by next-generation systems designed to last for a century or more. Crucially, it would feature sophisticated AI for autonomous navigation, allowing it to react to discoveries far from human guidance as it ventures into the unknown. So, in this video, we'll explore why the lessons from the original Voyagers make this the perfect moment for their successor. We'll examine the profound cosmic questions Voyager 3 could answer, and how this mission could be the critical next step in humanity's journey to the stars. To understand the future, we look to the past. The story begins in 1977, when NASA seized a once-in-a-175-year opportunity, a rare planetary alignment. This grand tour allowed them to launch Voyager 1 and 2 on a trajectory using the gravity of one planet to slingshot the spacecraft towards the next. This cosmic billiards technique was essential. Their tour of Jupiter, Saturn, Uranus, and Neptune returned data that transformed planetary science. We saw active volcanoes on Jupiter's moon Io, a first beyond Earth. They revealed Saturn's rings as a complex system of braids and spokes, and gave us our first look at bizarre worlds like Neptune's moon Triton. Each flyby rewrote the textbooks. Once their planetary missions ended, the Voyagers kept going. In 1990, Voyager 1 captured the iconic pale blue dot image, a humbling portrait of our world from 6 billion kilometers away. Today, it is more than 24 billion kilometers from home, the most distant human-made object. Both probes have now crossed the heliopause, the invisible boundary where the sun's influence ends and interstellar space begins. For the first time, we are directly sampling the galactic environment. But here's the challenge. The Voyagers were never designed for this. Their plasma detectors are limited. Their magnetometers lack resolution. And their data trickles home through faint transmitters. Each year, engineers shut down more systems to conserve what little power remains. This is where the case for Voyager 3 becomes clear. A modern probe could be built with instruments specifically tailored to the interstellar medium, measuring plasma density, charting cosmic ray fluctuations, and mapping magnetic fields at far higher resolution. With AI-based navigation, it could adapt autonomously to unexpected conditions. With improved nuclear power systems, it could operate long after the original Voyagers fall silent. In essence, it would not just extend a legacy, it would begin a true exploration of the region the Voyagers only glimpse. The vast expanse between the stars isn't empty, it's the interstellar medium, a complex mix of gas, dust, and magnetic fields that forms the very fabric of our galaxy. Why is studying this environment so critical? Because it's the cosmic ocean our solar system is constantly sailing through. Its properties directly influence our home, making its study essential for understanding our place in the universe. Our first line of defense is a creation of our own star. The sun's solar wind, a supersonic stream of charged particles, carves out a colossal protective bubble called the heliosphere. This bubble extends far beyond Pluto, acting as a vital shield. It deflects the most dangerous high-energy galactic cosmic rays, particles from distant supernova that would otherwise bombard the planets, posing a significant threat to life and technology. But its true structure remains uncertain. Is it a long teardrop trailing behind the sun, as long thought? Or is it a more compact, almost spherical shape, compressed by the galaxy's magnetic field? Some models even suggest a dynamic, fluctuating structure that constantly changes. Without more data, these compelling theories remain speculation, leaving a fundamental question about our solar system unanswered. Voyager 1 and 2 provided the first hints. As humanity's first emissaries to interstellar space, they sent back revolutionary data. But their observations are sparse, like trying to map an ocean from just 2 buoys. Their paths are single lines through a vast three-dimensional space. To get a global picture and fill in the monumental gaps, a dedicated mission like a conceptual Voyager 3 is needed. With modern detectors, a new probe would be a game changer. It could measure plasma density at fine resolution, track how cosmic rays penetrate the heliosphere, and map magnetic field variations across its boundary layers. This isn't just about collecting more data, it's about collecting the right data with a sensitivity far beyond Voyager's 1970s technology. It would turn our current blurry sketch of this region into a detailed, high-resolution map. These insights would refine models of how our solar system interacts with the Milky Way. But there are also practical reasons. Understanding radiation and plasma conditions is essential for designing future spacecraft, especially if humanity ever attempts interstellar travel. Knowing where regions of calm or turbulence exist could influence shielding requirements and navigation strategies. Mapping this environment isn't just academic, it's a matter of survival for protecting sensitive electronics and future astronauts from harsh cosmic radiation. Just as ocean currents shaped the routes of early explorers, patterns in interstellar plasma may one day guide missions to nearby stars. On the theoretical side, a new probe would also test competing ideas about cosmic ray transport and magnetic field structures. Observations of galactic radiation gradients, particle acceleration, and boundary turbulence would allow scientists to compare data directly with astrophysical models. This would provide the ground truth needed to validate some theories and discard others, settling decades-long debates. In this way, it would bridge theory and observation, turning speculation into evidence. The knowledge gained would be twofold. It would provide a definitive understanding of our own local environment, the protective bubble that makes life on Earth possible. But the implications are broader. The heliosphere is our accessible example of an astrosphere, a bubble common to countless stars. By understanding our own, we gain invaluable insight into the environments around other stars, informing our search for habitable worlds and deepening our comprehension of the processes that shape the cosmos. The significance of Voyager 3 extends far beyond data tables. Practically, it would act as a pathfinder, venturing into the cosmic ocean to chart a safe course for future exploration. Just as early maps charted seas and currents, Voyager 3 would create the first detailed atlas of interstellar space near the Sun. This high-resolution, three-dimensional map would reveal the weather between the stars, charting magnetic field lines, the density of interstellar dust, and the flow of the interstellar wind. This interstellar cartography would be invaluable, providing mission-critical information for engineers. Knowing the radiation levels and micrometeoroid risks is essential for designing the shielding of future robotic probes, or even one day, crewed starships. This data would inform the very architecture of interstellar travel, making it safer and more efficient. Culturally, it would continue a tradition begun in 1977 with the Golden Record, a profound message of cosmic communication. Curated by a committee led by Carl Sagan, the original discs carried sounds, music, and images of Earth. From whale songs to Bach and greetings in 55 languages, it was a message in a bottle, a hopeful portrait of humanity sent out to any civilization that might encounter it. Today, a new archive could be digital and exponentially more comprehensive. With modern data storage, it could contain our complete genetic code, vast libraries of art and literature, and scientific knowledge about our planet. It might even include AI-generated messages, crafted using mathematical principles to communicate without language barriers. It would be both a scientific payload and a cultural time capsule. This new emissary would be a snapshot of who we are in the 21st century, our achievements, our challenges, and our enduring hope to connect with the cosmos. Timing adds urgency. The Voyagers benefited from the last great planetary alignment. Similar configurations which enable slingshot maneuvers for speed will occur again in the coming decades. But missing them could mean delaying such a mission for a lifetime. For many scientists, this makes the case clear. If humanity wants to send a true interstellar probe soon, the opportunity must be seized. Meanwhile, NASA and other space agencies are studying related concepts. One prominent idea is the Interstellar Probe, a proposed mission that could launch in the 2030s or 2040s and travel far faster than Voyager, reaching the helipause in about 15 years. A Voyager 3 mission could either complement or evolve into such efforts, ensuring continuity between past achievements and future exploration. Together, these arguments highlight why scientists see it as more than nostalgia. It would be a step forward, practical, cultural, and symbolic. Voyager 3 wouldn't just repeat 1977. It would push deeper into interstellar space, refining science, testing future missions, and carrying humanity's story to the stars. The first Voyagers became our messengers. This one could be our new voice beyond the sun. Shouldn't we launch it? Are we ready to launch humanity's next great journey? Heat.